Split-cycle engines separate the 4 strokes of intake, compression, power, and exhaust into 2 separate but paired cylinders. Many configurations have been developed, but none have ever matched the efficiency of conventional engines. Split-cycle engines have had 2 major problems: breathing and thermal efficiency. The breathing problem was caused by high-pressure gas trapped in the compression cylinder. The low thermal efficiency resulted from compressing the gas twice. The Scuderi split-cycle engine solves both problems with its unique and patented concepts. Possibly the single most important breakthrough of the Scuderi design is firing after top dead center. Although normally considered bad practice, in a split-cycle arrangement, firing after top dead center eliminates the losses created by recompressing the gas. The big problem was really how to fire after top dead center. In the Scuderi engine, this is accomplished by using a combination of high-pressure air in the transfer passage and high turbulence in the power cylinder. The result is a split-cycle engine with better efficiency and greater performance than a conventional engine. On the intake stroke, the intake valve on the compression cylinder opens when the piston is at the top of its travel, or top dead center. The volume in the cylinder increases as the piston travels from top dead center to the end of its stroke, or bottom dead center. Air is pulled into the cylinder at low pressure atmospheric. Once the piston reaches BDC, the intake valve closes and the piston begins its upward stroke. The volume in the cylinder decreases as the piston begins compressing the trapped air to higher pressures. When the pressure in the compression cylinder reaches approximately 50 bar, the crossover inlet valve opens and the high-pressure air is pushed into the crossover passage. The intake valve opens when the piston is at TDC, and the pressure in the cylinder immediately returns to atmospheric, and the process repeats. The crossover outlet valve opens when the power piston is almost at TDC. High-pressure air, 50 bar, from the crossover passage enters the power cylinder. The power cylinder, now at 50 bar, begins its downward travel, the power stroke. Fuel is injected into the power cylinder, and combustion begins at approximately 10 to 14 degrees after TDC. The crossover outlet valve closes, and pressure in the power cylinder increases even though the volume is also increasing. The piston continues down on its power stroke, with the volume continuing to grow and the pressure now decreasing. The piston reaches the bottom of its stroke, BDC, and the exhaust valve opens. The pressure in the cylinder is now at atmospheric, and the exhaust gases are pushed out of the cylinder on the upward stroke of the piston. The piston reaches TDC, and the process repeats. The net energy produced by the Scuderi split-cycle engine is the difference between the 2 pressure-volume curves. The compression and power pistons are arranged on the crankshaft so that the power piston leads the compression piston by about 20 degrees. This enables the compression piston to begin pushing compressed air into the crossover passage as air from the crossover passage is moving into the power cylinder. The same amount or mass of air moving into the crossover passage from the compression cylinder is also leaving the crossover passage into the power cylinder. The process is similar to a marble in, marble out concept. Picture a tube filled with marbles that is open on both ends. When one marble enters at one end, it pushes a marble out at the other end. In fact, the air pulled into the engine during the intake stroke is not the same air used in combustion during that rotation of the engine. The air must work its way through the crossover passage to eventually be used in combustion. This process enables the crossover passage to remain at a relatively constant pressure and minimizes pumping losses through the crossover passage. In the Scuderi split-cycle engine, the crossover passage provides an opportunity to cool the intake air after it is compressed. This gives our engine a very high resistance to pre-detonation or knock. We can boost our engine to over 2.5 bars of pressure, while a conventional gasoline engine can only boost to about 1.5 bars before pre-detonation occurs. The result is an engine with significantly higher torque and power. In fact, our engine has the torque of a diesel, but can run at the speed of a gasoline engine, which means our engine's power output is almost 70% higher than a conventional gasoline engine. The Scuderi air hybrid engine is the first hybrid system that makes sense. Because the Scuderi engine is really a compressor on one side and an engine on the other side, it simply requires the addition of an air storage tank and some controls to convert it into a hybrid system that can recapture and store energy that is normally lost during the operation of the engine. Here are examples demonstrating how compressed air can be utilized as an energy storage device. Air is compressed and flows through the crossover passage and is utilized during combustion in the power cylinder. The power cylinder is turned off while the vehicle remains engaged with the engine. The force of stopping the vehicle continues the engine pumping, compressing air into the storage tank. The compression cylinder is turned off, and the power cylinder is fed pressurized air from the storage tank, eliminating the losses of compression. The compression cylinder takes in a charge of air that is only partially used by the power cylinder. The rest of the air is used to charge the storage tank.